Good afternoon, everyone. We'll give everybody else a few more minutes to join, but while we're doing that, we'll get started with some introductory slides. So thanks for giving up your time and coming to this webinar today. Today, we're looking at some innovative applications of weather and climate data in the energy industry. And we've got a range of speakers from across the public and private sectors who, I'm really looking forward to seeing their presentations and where they've used weather and climate data. So next slide, please. So just top tips on Zoom. So we will be taking questions for the speakers throughout the talks, and then we will be answering these questions at the end. So that's after all of the speakers have spoken. And could you please put any questions you have in the Q&A box rather than the chat? So this should just be at the bottom of your screen. Next slide, please. And then if you're having any issues with Zoom, you can make the PowerPoint slides bigger by closing the chat and enlarging the screens. And if you're having any technical issues, just try a different browser, basically. Next slide. So just an introduction to RMET and the energy sector. So I am currently the Science Engagement Fellow for Energy for the Royal Meteorological Society, which means that I lead the development of a program of different events, briefings, and training. So this could be sort of webinars like this, but it could also be blog posts and different training material. We also publish a State of the Climate for the UK Energy Sector report, and we're hoping to start our second report looking at the impacts of weather and climate on the energy sector over the last winter soon. And in doing this, RMET hopes to act as a bridge between the energy sector and the weather and climate communities. And one of the main ways we act on this is through the Energy Special Interest Group, which meets 3 to 4 times a year to discuss how RMET can best support the energy sector in this. And this is led by David Brayshaw and Daphne Sibniotti. And then on the RMET side, we've got myself, Hannah Mallinson, and also Beth Woodhams. Next slide, please. And yeah, there's more info there if you want to scan that QR code. Cool, so the program for this afternoon, just realized how small that is. So first up, we have Katie Chawinetchuk, who will be talking about applications of Met Office data for quantifying climate risk for the energy industry. That will be followed by Nick Leach from Oxford University and Climate X, talking about applications in the private sector. Following that, we'll have Lizzie Brock from Atkins Realis, talking about how weather and climate data is used to quantify risks for the nuclear industry. And finally, we'll have Professor Sean Wilkinson from Newcastle University, who will be talking about energy sector resilience and how we can understand this better with weather and climate data. Following that, we will be taking all of your questions for about 20 minutes before we close the event at 3:25. Next slide, please, Catherine. So if you're interested in any of the outputs which RMET produces, you can sign up to the Met Matters newsletter, which is the enthusiast blog for all things weather and climate. And they have lots of different things going on there, so do check that out if you are interested. Next slide. And just a reminder that if you're not already a member of the Royal Meteorological Society, then doing so can provide you with a variety of benefits. So you get a print and online copy of the in-house journal Weather. You get access to early discounts to conferences and also the range of publications which RMET produces, and potentially access to apply for support grants. Like me, if you're an early career researcher and you want to travel to conferences, but you might not have the funding to do so. So again, please do check that out. Next slide. Finally, we have the membership and accreditation schemes. So these are professional accreditation schemes where you can get certified for your skills in the area of meteorology. So there's 2 levels to this: the chartered meteorologist, the CMET, and the registered meteorologist. So again, do contact membership@rmet.org if you are interested in these. So I think that's our final slide. So without further ado, I will introduce Katie. So Katie is a manager of the industry science and consultancy team at the Met Office. In this role, she leads a team of scientists and consultants in developing weather and climate services for the water and energy sectors. Take it away, Katie.
Perfect, thank you. Thank you very much, Ben, for the introduction. So I'm just going to start by introducing our team at the Met Office. So the purpose of the industry consultancy team is to support the integration of cutting-edge statistical modelling techniques and the latest weather and climate science and data into industry decision processes. So we predominantly work with the water and energy sector, supporting them in questions related to operational efficiency, safety and resilience. Because of this, we work across a broad range of timescales, from short-term forecasting all the way out to seasonal and climate change projections. Our work then sits in this crossover between industry requirements and Met Office capabilities. We do also work in that other intersect in the Venn diagram with government, where it intersects with government priorities. But this is where we can use our expertise that we've gained from working directly with the water and energy sector to support relevant policy making decisions, such as those related to water and energy security. So today I'm going to provide some examples of work that our team, who I try to acknowledge some of the names of the people that have been part of these projects at the start of this presentation, are doing to support the energy sector in terms of integrating the best weather and climate data to support decisions that are related to energy security and also network resilience. So I think we're all aware that with the transition to net zero, the need to integrate weather and climate data is becoming increasingly significant. This is due to both the increased sensitivities of the system, due to the penetration of renewable energy, but also due to the changing climate, meaning there's a greater exposure to more severe events that can challenge the integrity of the system. So ensuring energy stakeholders have access to the right data sets so that they can properly robustly stress test their systems has never been more important. So I'm going to provide two examples today of work that we're doing. And the first example relates to decisions that impact the supply-demand balance. So the Met Office have been working with NESO on an innovation-funded project to support teams within the organisation in identifying the best weather and climate data for their power system modelling. This project was structured in 4 phases. The first phase of the project really focused on mapping the current weather and climate data that core teams within NESO were using for power system modelling. This enabled us to identify any common themes and limitations in the application of the data. The next phase involved developing a set of short demonstrator projects in order to support them in understanding the potential improvements of incorporating different methods or data into their modelling processes. And the final phase is a set of recommendations, but tailored both specifically to the 5 focus teams, but also trying to tease out what the common themes and potentially broader benefits to the energy sector. So this is just an example of how we map the decision processes and data pipelines for one specific NESO partner team that we were working with as part of this project. And by doing this for all the different teams that we were working with, we were able to pull together a simplified pipeline demonstrating the decisions that are being made at different lead times across the different teams, and also the climate data that's being used to inform these decisions. So as you can see, the decisions range from anything from out to 2 weeks ahead all the way out to 2050. But these decisions are predominantly based on historical data sets, either station observations or reanalysis data. So the next phase of the project involved developing a set of short demonstrators to highlight limitations in current approaches and the benefits that could be attained from changing their processes and incorporating new data sets. So in the first work package, as I just mentioned, we identified that a lot of teams' decisions are based on historic data. However, there are a number of limitations associated with this approach in terms of only using a limited data set to understand the risk of extreme events, but also some of the historical observations may no longer even be relevant due to climate change. So to overcome these limitations associated with the lack of real data, the Met Office has used its decadal prediction system, referred to as DEPRESIS, to provide multiple simulations of the current climate. This is often referred to as the unseen method. So for this particular case study or demonstrator, we have supported the gas team within NESO to actually integrate this data set into their decision process. So the gas team use a metric called the composite weather variable, which is essentially an index related to the temperature and the wind speed. And this index is then highly correlated to gas demand. So the graph that I'm presenting today shows an analysis of the duration of peak gas demand events, which are defined as when the CWV composite weather variable drops below a certain threshold. And we're then looking at how long that composite weather variable remained below that threshold. And what we've done is we've plotted a PDF of these events and the duration of the events if you just use the ERA 5 reanalysis data set to understand what the duration of these events could look like versus on the right hand side the DEPRESIS data set. So as you can see, the PDF using the DEPRESIS data set is much smoother. So that gives us much more confidence in the distribution of plausible events. You can also see that there are much more extreme events that haven't been observed in the historical record, but are essentially plausible in today's climate. So the project culminated in a set of specific recommendations for each of the NESO teams, but by doing this process, we've also been able to identify common themes and recommendations. These include the consistency and the use of historical data sets. So we really want to make sure that all teams are using the same data set and the same protocols so that we can make their decisions more reliable and also more reproducible and comparable. Incorporating enhanced climatological data sets so that you can capture plausible extreme events more robustly. Incorporating climate change, as we highlighted already, most teams' decision processes are forward planning, but their processes are very heavily reliant on historical data. The incorporation of forecasts at longer lead times for teams that are making decisions ranging from 2 weeks to 10 years ahead. And finally, the development of a modular NESO weather to energy conversion model could provide the flexibility that the different teams require in terms of different models that they need, but also be able to integrate new weather and climate data sets into their decision processing more easily. So the second example I'd like to present today is related around ensuring a resilient network in terms of understanding asset and network faults related to different hazards such as temperature and storm events. So UK electricity companies are required to collect data on faults, and this is stored in the NAFIRS database, so the National Fault and Interruption Reporting Scheme. This data set includes information on fault location as well as cause of the fault. So this is a very simple graph that we've plotted, analyzing the faults on the network between 2010 and 2019. The number of faults are grouped by season and also hazard. So as you can see, in the summer, lightning has the biggest impact on the network, whilst in the winter and autumn, it is storm events, so related to hazards related to wind and gale. Interestingly, what I found very interesting is the impact on the network in terms of the number of faults during the summer due to lightning is very similar to the magnitude in the winter due to storm events. So at the moment, the energy sector tends to use recent historic storm events to assess the resilience of the network. As I was talking about in the first example as well, using a limited historical record and using too few storms is a massive issue in terms of robustly stress testing your network. And there's a big risk that a high impact event is going to be missed. But also, we do recognize that using all of the climate data that is currently available to run in downstream impact models is often impractical. So we're therefore working with the energy sector to develop a framework to support an approach that makes use of all this data, but teases out the appropriate scenarios that need to be used to properly, robustly stress test the system, both in today's climate, but then in future climates. So the first step is to identify the hazard, so whether this is windstorms or lightning. And the next step is to then further categorize different features of the hazard that are going to cause an impact. So this can be done in a quantitative way using, for example, impact modeling, but also using more of a co-production approach and stakeholder engagement to identify features that are known to impact the system. So that, for example, within storm events, you might be thinking about the concept of a storm having an unusual direction impacting the system more because it's used to the prevailing southwesterly wind direction, or also taking into account, say, consecutive storms hitting the network. We can then create a data set that is effectively a subset of all this climate data, but we know is going to robustly stress test the system. And this will be based on historical events, but we can then also start to integrate enhanced climatologies and also climate projections to provide stress testing scenarios for future climates as well. So this is just an example of some work that we've been doing to pull together an initial demonstrator to support the understanding within the energy sector of the importance of using more data to inform the stress testing and the limitations of the current approach. So here we have used ERA 5 reanalysis data to analyze historic storm events from 1979 to 2022. We've then filtered these storm events, so we're only looking at those in the 98th percentile, well, gusts in the 98th percentile, and further categorized the subset of storms within that which had an unusual bearing. So what you can see in this graph, with the two graphs on this slide, is a wind row showing the average wind direction at the time of the maximum gust of the storm track. So the graph on the right is the wind rows if you only use recent named storms, whereas the graph on the left has used data back to 1979. So as you can see, with the recent rain named storms, you're severely underrepresenting high wind gusts that you could get from unusual directions. So in conclusion, I've presented two projects related to energy security and network resilience. I think it's important to highlight at the moment when stress testing these systems, the branches tend to be considered quite separately. So there are some pros to this approach in terms of simplifying the modeling and the data pipelines and being able to support specific teams' decision makings. But we also know that the weather events that cause these types of stress events are not necessarily independent. So some work that we're also looking to do with the energy sector is to develop guidelines to support a more robust approach to stress testing systems with a much more consistent use of baseline climate data sets that could support a much more joined up approach to stress testing.
That's great. Thank you, Katie. So just a reminder for people that might have joined during Katie's talk, if you have any questions, we're going to take these at the end. So please put these in the Q&A boxes throughout the talks, if they just pop into your head. So next we have Nick Leach. So Nick is a climate scientist at ClimateX, where he specializes in quantifying the impacts of climate change on storm systems around the world. Nick also works as a postdoctoral researcher within the Predictability of Weather and Climate Research Group at Oxford University, where he completed his PhD in 2023. Okay, all yours, Nick.
Can you see my screen all okay?
Yeah, that looks good to me.
Brilliant. Yeah, so, and you can hear me okay?
Yeah, I can hear you just fine.
Great. Yeah, so yeah, I'm going to be talking about my work that I do, mostly focusing on kind of the industry work that I do. So I work in a company called ClimateX, part-time and part-time at the University of Oxford. And so I'm going to be giving a very broad overview of the kinds of things that we do at ClimateX and the use cases that are basically our clients, what our clients are using our data for relating to the energy sector. And yeah, this is going to be a pretty broad overview. I'm generally speaking more comfortable talking about the science itself rather than kind of the use cases and that sort of thing. But I've engaged with our commercial team to get a feel, to give you a bit of a flavor of how people are using weather and climate data in a way that's relevant to the energy sector. So just to give a kind of brief overview of who Climate X, of what we are, because I'm sure that not everyone has heard of us. So we are what has kind of become known as a climate risk analytics provider, with a focus on physical risk and also a little bit on adaptation and resilience. But so what this means is that we provide information to the financial sector, so primarily large banks, and that was kind of the focus market that was decided on when the company was founded. But yeah, we provide information about how the physical assets that large financial institutions, most banks, care about, so basically things like mortgages, how they are how their exposure to climate change through those physical assets is going to change into the future. So basically understanding the risk to individual assets, both in the present and into the future. And so that the way that we often kind of, well, in a catch-all sort of very broad sense, we call this kind of Google Maps for climate change. So the idea is that a client, so someone in a large bank that wants to understand their exposure to climate change, will put in the coordinates or the address of an asset they're interested in, and then they'll use our data to understand, well, these are the potential losses from physical risks now, so weather-driven physical risks at the moment, and these are how they might change into the future, kind of trying to assess it in a way that's consistent with the state of the art in climate science. And so because these major banks tend to have kind of global coverage, a real challenge, which I'll talk a little bit more about later, is that they want you to provide data on global scales. But as I'm sure many people are aware, local contexts are really important to be able to accurately quantify these risks. And so that provides something of a kind of a conflict in what we do. Right. And so what do we actually do? And again, this is a very kind of brief description of the workflow, but we largely focus on extreme weather. So as Katie mentioned, like focusing on extremes is kind of makes sense in this context, because in terms of physical risk for many hazards, most of the drivers of physical risk come from your extreme weather events, not from your kind of day-to-day weather events. And so what we do, we tend to start from weather and/or climate data. So using historical weather data to try and assess risks at the present, and then use data from something like climate models to try and understand how that risk might change in the future. Perform some sort of extreme analysis, so that might be like leverage things like extreme value theory, to understand, well, can we quantify things about these extremes? And again, the kind of themes of what Katie was talking about, so the requirement for large samples to try and actually accurately assess extremes is super important for what we do. And then we use this kind of weather and climate analysis, which is usually the starting point, to drive hazard models. So one example for that might be, well, if you want to understand flood risk, you can't just look at rainfall. You need to actually use models to understand, well, if it rains this much, where is the water going to go, and like what locations might get flooded? Because like you can have very high rainfall, but if your asset is at the top of a hill, it's much less likely to be flooded. And so you have to take that into account as well. And that's where the local contexts are typically incorporated. So some hazard models might also leverage things like machine learning. So for some types of peril and natural hazards, particularly geohazards, where there's there's basically very little data on the scales that we need to provide things like global coverage to run physical models of geohazards. So that for those contexts, we often incorporate kind of machine learning approaches. Right. And so once we've used these kind of models to try and assess the kind of physical hazard, so that might be flooding, we then try to estimate associated losses, because at the end of the day, that tends to be what our clients are interested in. And that's those are the figures that they then take and put into their own models and use for decision making. Is not, well, the likelihood of a storm is going to change from now into the future. Is actually, this is how much your losses due to that storm are going to change from now into the future. And so next, I'm going to give a brief overview of the types of data that we use. I mean, I think probably among all of the presenters, that it's going to be a pretty similar mix, but basically saying that as a provider of physical risk, you kind of have to use more or less all the different types of data that are available in terms of weather and climate. So these range of things like weather reports. So for the US, there's things like the NOAA storm reports data set, which has some kind of quantitative measurements, but also just basically reports of storms, but they are extremely useful. Direct observations, so that's things like station data. Reanalysis, which will be probably pretty ubiquitous in kind of the weather and climate risk industry, so things like ERA5. We use a lot of remote sensing. So this can be things like satellite-derived rainfall products, down to things like land use cover that is very important to accurately model flooding. We use forecast model data. So Katie talked about the unseen approach. That's something that we use as well in our tropical cyclone model, which this figure here is kind of showing 3 different types of data. So this figure has tropical cyclone track data from IB tracks from ERA5, and then kind of unseen tracks based on a weather forecast model. And then the final type of data that is kind of crucial is climate model data. So this could be global model data or regional model data. And so now that I've kind of given a very brief overview of what we do and a bit how we do it, I thought I'd give 3 case studies and then very quickly plug my own research at Oxford. So the first case study, the 3 case studies, I'm giving a sort of 3 different types of effectively client or like use case of our client. So the first one might be a major bank that has invested or is interested in investing in renewable energy assets. And so what they want to do is they want to understand the physical risk of those assets across the lifetime of those assets. So things like wind turbines often have expected lifetimes on the order of decades. And so if climate change is going to increase the risk of a particular asset into the future, then banks want to know and want to be able to account for that in terms of their books. And so these 2 approaches, so the stuff that they already have on their books is usually known as back book. And so that's one way in which they use the data, and the things that they are interested in sort of investing in is front book. And so these are treated differently, but they're kind of 2 ways in which banks might use our data to get information about using the underlying weather and climate data to understand the risk to assets that they're interested in. The second use case is asset managers or kind of real estate developers who are interested, usually rather than being interested in specific assets that they either are looking to buy or have already bought, they're interested in large kind of areas of land and wanting to understand kind of on a broad scale, what is the risk if I'm going to develop this land for the purpose of renewable energy, so wind turbines, solar farms. What are the potential risks that are already in play, and how are those going to change into the future? And so the final use case that I wanted to briefly go over is on kind of, again, talking about banks who might have interests in commercial properties, is understand, or like basically all potentially investors who have interests in basically companies, and understanding how those companies might be affected by weather-related business disruption. So one example of that would be if you're a shop and you rely on electricity to stay open. If your nearest major substation is at risk from a weather hazard like flooding, then kind of down the chain, the banks want to understand, well, how many days of disruption could we expect this company, this shop, to be subject to based on the weather-related risks to their local substation. And that's kind of the third case study that I wanted to talk about. And so finally, just to give a list of kind of the challenges in this industry. As I talked about, there's a real conflict of scales, because basically at the end of the day, the banks and the financial institutions typically operate on very large, like continental or global scales. Whereas as I'm sure many of you know, to kind of fully understand the risks at asset level scales, those 2 things kind of don't it's incredibly difficult to manage those 2 conflicts, because it is, at the end of the day, it's kind of too time consuming to overly focus on any one area and to understand one small area incredibly well when you've got for our clients, we need to understand kind of at a global scale. And so this is somewhere that things like machine learning can help. For example, doing things like identifying flood defenses that are not contained in openly available data sets that can improve your kind of the local contextual knowledge that you have to be able, but also to be able to apply it on a global scale. This kind of global coverage also means that there are major coverage gaps if you kind of depend on very high resolution data sets, because think places like Europe and the US have an absolute wealth of weather and climate data at very high resolutions and very high kind of fidelities. But other parts of the world really don't. So places like the global south, so Africa, and often parts of Asia Pacific have far kind of less available data. And so you have to make the choice between having really high fidelity data in some places and much lower in others, or to have more consistent data kind of everywhere. Another challenge that I think kind of is particularly important for the energy sector is in the types of extremes. So climate models basically, well, they don't resolve some of the most relevant types of extreme of the energy sector. So I'm thinking about hail, I'm thinking about convective storms, which are very important for solar, particularly for solar risk, but they're not represented in climate models. And then the kind of last point I'm going to say before moving on quickly is on kind of, there's another challenge that we have when engaging with clients is there's a huge amount of education that has to be done, which when you're engaging with people that aren't familiar with kind of the science under like climate science, essentially, you have to basically get them comfortable with a lot of the uncertainties that are inherent, and getting people in the banking sector comfortable with those kind of uncertainties can be a real challenge. And so that's something we have to spend a lot of time doing. And so that kind of wraps up the Climate X focus sector. But I also wanted to, which I think is kind of particularly interesting given what Katie was talking about in the second half of her talk. So at Oxford, I study extreme weather attribution. And so we have been working on an approach to basically answer climate-related questions using weather forecast models. There's a bunch of reasons why you might want to use weather forecast models for understanding how climate change is going to impact weather extremes that I'm not going to go into here. But basically what we've been doing, and so one particular piece of work that I'm going to talk about here, is that we have been trying to understand what the potential losses during Storm Eunice were. So using an ensemble weather forecast, run those through a loss model, and then use that ensemble to understand, well, the losses were this much, but they could have been potentially much more, potentially much less, just because of kind of how the weather itself unfolded. But this approach doesn't just try and look at current weather forecasts, but it also tries to reinitialize those in a future perturbed climate, so a warmer climate where you've increased ocean temperatures and changed the amount of carbon dioxide in the atmosphere. And when you do that, you get another forecast ensemble that has a different set of storms that might happen in, say, a future climate. And so we found that one kind of particularly, I mean, again, not getting into anything probabilistic, because it's so far into the tail that it's very difficult to robustly quantify anything probabilistically about this. But there's one particularly interesting storm, which when you put it through basically a loss model from an insurer, produces European losses of kind of approaching 50 billion euros, which is kind of historically unprecedented, and something that I thought was kind of potentially particularly interesting for the energy sector. And if anyone is interested that is listening, please get in touch. Is that the kind of the footprint of that storm, which is the figure you can see here, has a particularly strong, like it intensifies particularly over an area of very high wind turbine development. And so it might be interesting to basically use this to try and to almost stress test the wind, like basically the wind, some of the wind farm developments that have happened in Europe. And with that, I'm going to finish. And here are contact details if you're interested in any of that. But thank you.
Interesting stuff, Nick. Thanks. Cool. So next up, we have Lizzie Brock from Atkins Realis. So Lizzie is a principal climate adaptation consultant at Atkins Realis, where she delivers bespoke weather and climate solutions for resilience plans and daily business operations. She previously worked at the Met Office, where she specialised in radar R&D. Lizzie gained her PhD in microwave photonics from the University of Exeter in 2013. It's all you, Lizzie.
Thank you very much. The audio is working. Thank you. And you will notice my PhD has got nothing to do with what I do now. Good afternoon, everyone. I work for Atkins Realis, who are an international engineering firm. We have clients across energy, water, any kind of main work, civils, transport type projects, you name it, we build it. We build it internationally. I'm going to be talking to you today a little bit about our work supporting the nuclear industry and people who are, or companies and businesses who are providing nuclear power, particularly in the UK. So thanks very much. I'd also like to thank my colleagues Stefan and Tracy as well for their work, some of which I've used in this slide deck. And yeah, I hope I do okay following two excellent talks. So the problem, right? What are we doing? Why are we doing it? So at the moment, the UK generates power from power companies, and it also stores nuclear waste. Those are two very different things, but both of them are required to be climate resilient. The UK has ambition to increase its capacity of electrical generation fourfold by 2050 in order to reach their net zero targets. And most nuclear power stations are actually due to be commissioned by 2030 unless they get any life extensions. But overall, nuclear power is going to keep generating and generating waste, which also needs to be stored somewhere safely. So overall, the nuclear industry has a very low, what we call risk appetite. So for storage of nuclear waste, they are thinking of doing this underneath the ground. And because of the half-life and the nature of the nuclear waste, which is actually, anecdotally, because it has a half-life, it's actually classed as something slightly better to handle than things like waste from arsenic, FYI, which doesn't have half-life, it just remains terrible. So they're looking at generating these facilities and then the facilities running well into 2200 or further. And on top of that, the nuclear industry also has regulations from the ONR, which require them to look at 1 in 10,000 year events as your basic design basis. And the ONR also asks licensees to look at what happens in the event that a 1 in 10,000 year extreme event type is exceeded. So can the system still handle it, or does a sudden drop off happen so that your nuclear power station is suddenly in quite a bit of danger? So those are called cliff edge events. The ONR also asks that providers have an eye on reasonably foreseeable effects of climate change over the lifetime. So very much maintenance issues and not just extreme events. And also they require licensees to keep a watching brief, and it's word for word from the regulations there, on climate change and take into account advances in relevant good practice and update of their safety cases. So this is where they look their safety cases at their climate risks. So the two problems, as discussed by my peers, we don't have a huge observational data set or climate data set that's going to stretch to 10,000 years. So it means you have to make some statistical assumptions and calculations. And by having a regulation that asks you to look for a watching brief, it then also means that nuclear providers basically need to keep on top of the latest research that can plausibly be brought into some of their design considerations and looking at those potentially avoiding cliff edge events. So I've decided to focus today on a case study, the things that you have to consider when you are providing evidence and supporting a nuclear provider in going through these safety cases and keeping that watching brief, if you like. So overall, according to the Met Office, extreme rainfall events could be 4 times as frequent by 2080 compared to the 1980s. And drawing back to those timelines that are relevant for the nuclear industry, that's quite a lot. And the nuclear industry even has to look beyond that. So what's always a good place to start when you're looking at categorizing 1 in 10,000 year extremely rare events is actually stop and look at the data, see how that is categorized and see what's happened in the observational record. So I've included a few bits here on the right-hand side and draw your attention to the 2015 entry of 341 millimeters in one day in Cumbria that happened. Keep that number in mind, in a 24-hour period. So for extreme rainfall, a lot of the considerations are in that one-day period or in that sub 24-hour period. You heard Nick talking about how hard it is to forecast or model convective events. I'll talk about that again later, but that's certainly true. And it's those incredibly convective events where that actually start to generate those heavy precipitation events, those extreme rainfall events. So what do? You generate data via innovative sources. You end up with some more innovative data. Great. So there's two different ways of doing this industry standard. Well, there's many, many more, but I'm only going to present two of them today because these are the sort of the two front runners, if you like. One is calculating depth, duration, frequency curves from available data sources. So it's quite robust, but it doesn't include confidence intervals, which, let's face it, is quite important, because if we're trying to look at an event that hasn't actually happened, you can't put your hand on your heart and say, right, this has been observed. We haven't got 10,000 years of data to actually say that. It's all statistical analysis. So it's quite important that whatever you do, I think, has a confidence interval on it. So the other way of doing that is extreme value analysis. It's a method that actually started in the financial sector and has been used throughout. And this could be a talk in and of itself. It's several PhDs worth of talks in extreme value analysis. So the advantages of it are that it is a statistical technique to extrapolate and predict extreme values. It gives an assessment of uncertainty, but it can be quite dependent on how good the data is to be fed into it. And that's kind of the crux of everything. No matter how innovative the data methods are and the solutions that have come out are really heavily dependent on how good the data is going in. So it's always good to come back to the observations, looking at what's spat out of these methods. For instance, for the FEH handbook, you've got these 48-hour totals over 30 years and 100 years. And actually what's been measured in Cumbria is still very much quite high at 341, but that is definitely more than that 552 in half there. So it's all about taking a view, looking at your various different data sources and where they've come from, and then how your statistical view, however that's been calculated, actually compares. So one of the things that you would then have to do, so the whole point of doing a safety case is not to just look at rainfall, as I think weather and climate scientists we do quite often, but actually start to make that relationship into flooding. This is an excellent graph that was produced in 2021 by Hayley Fowler and her colleagues that starts to really show the integrated processes that go on when you have to start considering flooding. So you're not just using rainfall as your indicator of how many floods are actually going to happen, but how do we actually start to think about flooding itself instead of just rainfall. You can see there's quite a lot from ground and storm surges, the actual overall urbanization of the area, and then what's actually going on in the atmosphere up here. So I understand this recording will be made available later. So you can always go back and have a look at that graph. I've given the reference. Then you have the other challenge, which is climate change, right? So you've already got a set of data for how to calculate these particular really, really extreme events. Now you have to also take into account how climate change might change those extreme events. And that's also an unknown as of yet. We've got really, really good indications as to what they could be. But there are also, again, a variety of data sources. What I'm showing you here is a rule of thumb, if you like, on the left, which is the Clausius-Clapeyron relationship. So you can say that for every degree of warming, there'll be a 7% about increase in intensity of rainfall. But again, it doesn't give you an end flooding. Is my asset going to be flooded or not? You've also got the latest developments from the Future Drainage Project, which is something that uses UKCP 18. And you can see that then very much varies over the country, percentage-wise in increases of rainfall. So you have to take all of these different things into account. And then you also have to take into account how much science has matured behind each thing. This is yet another graph from Hayley Fowler, but I absolutely love it because this is showing a sort of a cross-sectional look at a really convective event. So you can see this great big hammerhead cloud that's come in here. And what's been developed in the same paper as before, by the way, the same reference, is not only a look at the processes that are involved, but how much the research behind it has been developed at that time, gone from very likely to uncertain, to give an idea about how much scientific consensus there are actually about these different processes and how well the climate models themselves are reproducing these processes to then be used downstream to understand how flooding has been put in. So as somebody who supports agencies who are having to actually make decisions against some of these requirements and taking a view of all of the evidence, these are the sorts of things that we might want to consider. And we always suggest going for a multiple strands of evidence approach in this way, because there's UK CP18 products, for instance, for the UK. But there's also other various scenarios, like for instance, H++ scenarios that were based on a previous climate modeling project, but they are still very much relevant. How those rain game projects are producing or are looking at flood events, horizon scanning of future research of high impact, low likelihood events. So very much some of the extreme work that Nick was talking about. And also recently that's just come out is the new EA flood and coastal erosion data as well. So you have to take a view on everything. But I think I've got 3 minutes left. So in that time, I'm just going to briefly show you what all that means. So downstream processes actually also produce innovative data points. So this is a little bit about inundation modeling. So one of the things that all of this rainfall research and weather research does is then produce or put the onus downstream, if you like, on providers to actually use the data. This is an example about how they actually use it. So they pull it into models. So my colleague has actually shown the different types of models that get used. You can go for 1D, 2D, and 3D models, and they get more and more complex. And they give better results the more complex that they are, or sometimes they don't due to processing. This is an example of a power station somewhere that will remain unnamed, but this is an actual flood event that happens at a power station that, you know, does have all of these checks and balances in place. But this occurred. Again, we're not going to say where. You can actually see the barriers that were put up on site and the flood waters coming in. So this is an example of what happens downstream of those really heavy rainfall events that we talk about. So these model inputs here, LiDAR, topographical survey, hydrological boundaries, and the weather data that we spend so much time really analyzing to see actually how close to observed does it get, then gets flung into these models to get actual flood mapping out. Then on top of the flood mapping, you have actual site data, which I find fascinating as well, because you start to get a site response and to see actually, is my asset going to be flooded in these events? So just to finish off here, there are things that we can do in weather and climate modeling, but I also think that also does come hand in hand with looking at those downstream processes. Actually, you know, the last lot of flood modeling that was pushed through by the nuclear industry actually happened because of the Fukushima earthquake event that happened in March 2011. And it had a lot of knock-on effects on the nuclear industry, and we're still seeing that today. If we were re-evaluating those particular models, these are some of the things that we would look at. We would look at the advancing methodologies and boundary conditions. We'd look at using additional gauge records. We'd also look at topographical structure changes, because that's a huge input into flood modeling. And of course, any advances in the actual hydrological software packages again. So in my final minute, my closing thought is really, in the case of planning for resilience measures, you know, could there be, and as a consideration, could there be more modern approach to flood modeling actually have more of an impact on the end result than a new set of rainfall values from climate or statistical modeling. These are the sorts of things that we would put through an engineering standard, which I think is what people have been talking about on these process diagrams. So it's something called adaptation pathways. So you're looking at thresholding throughout your processes. This is a defined engineering standard, something we do in our group and supporting our clients. And yeah, I'm going to leave you with that, because the answer to that question is site specific and customer confidential. So thank you very much for your time, and I look forward to your questions. Thank you, if you have any. Thank you.
That's great. Thanks, Lizzie. So we'll now move on to our final speaker. But just before that, another reminder that if you have any questions for any of the speakers so far, please do put them in the Q&A box down at the bottom. And so we can get to those just after Sean's talk. So Sean is a professor of structural engineering at Newcastle University with over 20 years of experience in modelling how natural hazards affect the built environment. He specialises in producing risk models for infrastructure networks, and he is currently leading the CS Now project, a research programme which uses the latest scientific knowledge to inform UK climate policy. Okay, all yours, Sean.
Can you hear me?
Yeah, we can hear
Can
you
you
just
see me?
fine.
Can you see my presentation?
Can't see your presentation just yet, but I imagine
hang
it's
on.
coming
Right,
in soon.
There we go. Is that, you seeing it now?
Yeah, that looks great to me.
Brilliant. Okay, thanks very much. Yes, I'm Sean Wilkinson. So I'm a professor of structural engineering here at Newcastle University, and I'm going to talk about using weather and climate data to better understand resilience in UK energy. So the first one there is just down the road from where I live. That's where I go running sometimes on a weekend, just north of Newcastle, and that's the damage that was done in Storm Arwen, or some of the damages that was done in Storm Arwen. And, you know, there's been a lot of things about whether or not this was an unusual storm and an unusual direction. This is some work with Colin Manning, who is one of the co-collaborators in the work that we're doing here. This is his paper where he's showing how the important one, let's turn on my laser pointer, is we have the return period of a storm, and this SSI is a storm severity index, so that can be thought of as a measure of, well, how severe the storm is, as the name says. And we can see in the future that they are getting, they're going to increase. But also, if we look here on the left, these are not only, this is current climate and this is future climate, but the types of storms that we're getting. So these dark blue boxes are storms that contain sting jets, and so we can see that not only are we going to get more bad storms, bigger storms, we're also going to get storms with more damaging features in them. So that was, we were doing this work before Storm Arwen, and I'll show you what we've been doing to try and sort of help the energy industry deal and prepare and respond to these significant events. So what I have here is basically a picture of what insurance companies do. They spend most of the time trying to get this graph. So on the horizontal axis, we have how much they pay out each year, and on the vertical axis, how often they pay out. So for example, this could be, this is a year with not many storms, and this could be years with a number of hurricanes hitting the US or Europe or whatever. And so you're trying to get some sort of curve that says how often you're going to pay out a little amount and how often you're going to pay out a large amount. And obviously, as we said in the previous Nick's talk, that we have lots of data here, which we're not that worried about, but we don't have a lot of data in the very extreme events, and these are the ones that actually we want to know about. And so that often, even if we do have some storms, we're not sure where on this horizontal axis those extreme storms sit, and so we need to do some model data to get that. Now then what they do is they work out the area under that curve, and they can get an average annual payout, and they use that to set insurance premiums. Okay, so just the distance between those two lines is their profit. And if they had infinitely deep pockets, that is all that they would have to do, because they would always win. But one, they don't have infinitely deep pockets, and two, they don't sit around with, what was it, 50 billion sitting in a bank account that they can bring out if a big storm occurs. And so insurance companies tend to buy reinsurance, and they have to figure out what is the loss that they can actually cover, and not go broke. Now, we're doing the same sort of thing with energy networks, only that very extreme event is finding out how likely something that is politically unacceptable will happen. We want to know the average annual cost of the impact, and we want to know what our resilience enhancements are doing in terms of our risk. So as we increase our spending on resilience enhancements, all these blue boxes start to shift to the left, and this yellow average line will also start shifting to the left. And once those two meet, well, then you've got an optimum system. So, so the way insurance companies do this is that they take a synthetic catalogue of plausible weather events, significant weather events. They change, that might be a storm severity index. They change that to an intensity calculation, which might be intensity of rainfall or wind speeds at different locations. And they overlay that spatial intensities over their insured assets. And those two go into a loss estimation model, and they use, based on those losses, they set the insurance premiums, the excess and the reinsurance thresholds. So what we're doing, what we're developing at Newcastle, if you look up in the top right-hand corner here, this is the disaster management cycle, where you prepare for an event, the event happens, you have an immediate response to try and put things back together, or minimize the disruptions. Then you start to recover, and in the longer term, you're trying to, in disaster management, they're calling it mitigation, but obviously in climate, we'd be talking about adaptation. So what we've been doing, originally, when we went to the electricity energy companies, we were wanting to look at climate change, but there were no incentives for climate to look at modeling climate change, but there were incentives for them to minimize the losses, the power cuts due to storms. So we started off with weather forecasts. They gave us their asset information. These weather forecasts can either be used directly, as we've been doing with wind speed, or you might put them into some sort of a model, like a hydraulic model, to get flood depths. Those go into the damage estimation model. And then this is where it differs, and this is why I call it consequence forecasting. It's still impact-based forecasting, but when you talk to insurance people, they stop here, okay? They're only interested in insurance payouts, and very often we're forgetting what are the consequences for the people on the ground. So we put in an extra layer there to try and figure out how are actually people, what experiences do people have due to this event. And in the case of the power companies, their contingency actions will be to put more people in the call centres. For their vulnerable customers, they will ring them up and make sure they're okay, and they'll put on more linesmen to fix the lines after they've blown down. Now, how do you get these two red boxes? Well, what you do is you do an aftermath survey. So after a storm, you take the weather observations and you run it through the model, and you use that possibly to make a better environmental loading model, or your damage estimation model and your consequence calculations. So first speaker talked about the NAFES fault database. Here's a snapshot from it, and they have about 100 different descriptions of things that can actually make things fail. And we can plot those to get where the hotspots are for damage. And we need to put those against weather observations. So what we've been doing is using the UKV T+0. You can think of this as being reanalysis data. And so on the right here, we're looking at South Wales. Each of these crosses is an output from the UKV model. The dark green lines and the red dots are energy infrastructure. And so we can start to look at, from the NAFES data, we can see exactly where a fault occurred, and we know exactly, well, we have a good estimate of what the wind speed that caused that fault is. When we put those together, these are fragility curves, which is what the insurance industries, when they talk about impact models or damage models. So each of these grey dots is a fault, and sorry, each of these grey dots is a storm. And so we can see, for example, at 27 meters per second, we had somewhere between 50 faults per 1,000 kilometers of line, and sometimes we had 0. So there's a lot of scatter between these, but we do have a lot of data. And so what we can do is we can actually start to put distributions through the different bins. So if we look through that slice, we can get a distribution. And not only can we quote median fault rates, but you can actually quote percentiles, 90th percentiles, or whatever it is, so that they know how or what our best estimate is, or what our most likely estimate is, but also put some confidence intervals on that. So here's some output from the validation case that we did, and we can see here this is a compound storm, and so so the red line is a weather forecast 24 hours before the event. The blue line is the reanalysis data, and the grey dashed line is predicted faults 24 hours before the event, predicted faults using the reanalysis data and the actual faults. So you can see the first storm rolls in, the second storm rolls in, we get some more faults, the third one rolls in, and then the fourth one comes in. And we can see that we're getting a reasonable sort of correlation between the actual faults and the reanalysis data, and not too bad as well when it comes to predicting 24 hours in advance. In fact, in this paper here, we found that 50% of the time we got to within about 50% of the number of faults that we predicted, within 50% of the number of faults that did occur. And so that's for an early warning system. We can also do stress testing. So Ofgem are very interested in getting stress testing to make sure that the resilience of the energy system is staying the same as the climate changes. And so we use exactly the same model, only this time we're using UKCP 18 climate projections. And instead of, and in this green box, we're developing or testing resilience enhancements, which is usually reinforcing the network. And then we can run that model and see what happens. We've done this in one of our projects using 3 time slices, one centered around 1990, one centered around 2030, and one centered around 2070. We've done it for 3-second wind gusts, hourly temperatures, precipitation, and we're not yet done lightning. So here's one of the results from that, and we can see on the horizontal axis we have the return period of a heat wave, and on the vertical axis we have CML, stands for customer minutes lost. So rather than we get faults in transformers usually from heat, we could put the faults, but actually the consequence is power cuts, and so CML is how many customer minutes were lost. And so we can see that a heat wave with a 10-year return period in the near future will be almost double the number of power cuts, and in the far future we're coming up to nearly triple. They quite like this Ofgem, because the other one is, if you think about a very significant storm, a heat wave rather, 1 in 50-year return period, then in the near future, instead of once every 50 years, we should be getting about once every 7 years, and in the far future, almost every year, a 1 in 50-year heat wave will be occurring about every year. So we've done the same thing for wind for different regions. And here we can see, for example, in the East Midlands, UKCP is projecting for the wind speeds to get less, whereas in South Wales, the wind speeds are getting greater. So we can look regionally at what are going to be the hotspots in the future. And we can do it for faults and customer minutes lost. And then neither of these are linear. So there's not a linear relationship between wind speed and faults, and there's not a linear relationship between faults and customer minutes lost. So yeah, so one isn't, you actually have to put it through a model to get the downstream effects. And so what we're sort of trying to do is to try and make this impact-based forecasting or consequence forecasting useful for decision makers. So if you just take the climate projection information, you can say the usual sorts of things, that windstorms are likely to increase in frequency and intensity. And that's the high level result. We can actually quantify this and say, for example, in South Wales in the far future, a 1 in 50 year storm will occur on average approximately every 20 years. If we use impact-based or consequence forecasting, we can have more useful information where we can say things like extreme windstorms are likely to increase in frequency and intensity over the UK. For example, in South Wales, for RCP 8.5, we are likely to see a 1 in 50 year return period storm resulting in approximately 30% more faults on the energy network in the far future, and a very extreme event, or an extreme event such as a 1 in 50 year storm, will occur on average approximately every 20 years. And yeah, so, and again, this is quite, the people who we're giving this to quite like that information because they can give that to their bosses, and they kind of get it, even if they're not engineers. Right, that's me done.
Great, thanks, Sean. So I'll invite all of our speakers to now turn their cameras on, and we've got about 15 minutes to go through a few questions. So hopefully we can have a good discussion here. Unfortunately, Nick has had to dash off to a different meeting, but I think the questions are broadly relevant to most of us. And yeah, just a reminder that we're taking questions in the Q&A box here. So I guess one of the first questions that came up was from Bruce Ingleby, and I'm not entirely sure who this is best addressed to, but I think each of you probably face challenges with the lack of observation data for specific hazards that you might be looking at, and how we might overcome this. But Bruce has said that he works on a simulation of in situ observations at ECMWF, and he's frustrated by the lack of access to hub height data from wind farms, particularly real-time data, which could be useful for improving forecasts of 100-meter or 60-meter wind speeds, given more observations. The wind sector use our forecast directly or indirectly, and obviously ERA 5. Is there a way that data availability could be improved? I guess we can probably go around the speakers and talk about different challenges that you might face with site-specific data. I don't know if you want to start, Lizzie, speaking about site-specific data for nuclear sites. The challenges.
Yeah, massively challenging, always challenging, because even if you have a really engaged client who has an enormous estate, so we'll put like loads of MET stations up, you then need to have people who have put those MET stations in the right places as well, in order to give you that really, really good data that you can then start to have high fidelity trust in. Yeah, so it is a problem. It is something that I think probably, I mean, personally, I used to work at the Met Office in Obs R&D. I do know there is a whole department there. Dr. Edmund Stone, I think, did quite a lot of opportunistic observations and looking at calibrations with that. But overall, I would love to see policy people like regulators actually saying, okay, you need to be putting what MET stations up on your premises if you're finding, especially for the nuclear industry where EVAs are so incredibly dependent on site-specific data, that you actually need to start doing some more measurements, if you like. But at the moment, there's not a push for it so much because the UK is actually very rich, very data rich in comparison. With some really lovely stuff coming from the NCIC, like the had UK Grid. So that would be my answer, to actually start to try and get the governing bodies to put something more in place, because it can't just be there to be used. It needs to be there, put in properly, and then maintained properly, which is can be a bit of a pickle. I don't know what other speakers think.
Yeah, I guess we can pass to Katie. I mean, how are sort of NESO getting around this? I think, like Lizzie was saying, we do actually have pretty good spatial data coverage in the UK, and I guess a lot of NESO's problems are nationwide, so maybe this is less of a problem for them. But I don't know if you had any thoughts on this.
I think it is definitely a problem, and I think we do need to be really careful with the reanalysis data sets, especially with their known biases and problems at capturing the wind speed, especially at height. One kind of way around it, which I think Sean kind of presented in the work that he's doing, is the UK V data. Just at least it's at a higher resolution, but we still need to make sure that it's capturing wind speed at height correctly, and to do that we need the OBS. So yeah, it's something that definitely, when you're doing any analysis, needs to be considered. And I think there are also there's wind atlases out there and other data sets where people have spent, other organizations have spent time creating these higher resolution data sets. But then for things like generation, when we're thinking about the supply demand balance, we do need this coherent data set of the wind speed with the other variables.
Yeah, because I guess often it's a challenge of, even if you've got your temperatures at a daily or hourly resolution, you'll also want your wind speeds at the same resolution as well, and then across your different sides. So yeah, that's always a challenge. I guess finally we'll go to Sean on this question. Yeah, I guess both of the speakers have touched on the fact that actually for nationwide problems there are plenty of data sources available, but I guess on these more local scales that you've been working at in South Wales, I don't know, are there any challenges there with identifying sort of specific components of a storm that specifically damage, I don't know, substations or other sites?
Yeah, so just going back to the data sets, I mean, in theory, if you've got an observation, that should be incorporated into the T+0 forecasts that we use, and so it should match that observation. Obviously, if you go up higher, you may not have an observation. I don't know the accuracy of these T+0s. I think Colin's done some work on them. I think they're pretty good. And then you've got observations on a 2-kilometer grid, and Lizzie was talking about HAD UK grid. We use that as well. It's assuming it's correct. It's a great product. It makes life very easy. So it would be good if the T+0s were just released in some sort of a data set. In terms of so what was the other thing you wanted me to comment on the features of storms and things?
Yeah, I guess how do you go about identifying specific parts of a storm, I don't know, sting jets or anything that might be causing these hazards at specific sites?
So at the moment, we're trying to get funding to do that very thing, to go back through the historical record and find out how much more damaging storms are with sting jets, and can we incorporate other features. So for example, again, Colin has done some work on wind direction, which has an effect, as does whether or not your storm is in summer or winter. So if it's in summer, it's more damaging for the same wind speed, and there's a few other features like that. Yeah, so that is a work in progress, but it does what we're trying to do. There's a huge scatter. We're trying to reduce that scatter down, for those on those fragility curves.
Cool. Thanks, Sean. I think we'll move on to the next question from Abhinav. So I guess maybe first this can be addressed to Katie, because you spoke about the use of seasonal and decadal forecasting data in your talk. So they ask, at what horizons, days or months ahead, are you usually able to make forecasts for extreme events? I don't know whether that's something that you've already done or whether it's something that you're perhaps looking to do in the future.
So with the work that we're doing with the energy sector, we're tending to focus on decisions, not the short-term forecasting decisions, but decisions with lead times from 2 weeks ahead to further ahead. So when you start looking at decisions at these longer lead times, there is an inherent level of uncertainty associated with it, but there is some skill in sub-seasonal and seasonal forecasts that you can tease out, especially if there is a specific, what we're doing is work, if you have a specific impact that you're interested in, you can then try and tease out where the skill lies at these sub-seasonal, seasonal timeframes to be able to better predict it. What you'll then be looking at is creating a forecast that is more highlighting whether there's kind of a higher risk or a lower risk at these longer lead times for these events to happen. You're not necessarily going to be able to tease out whether a specific extreme event is necessarily going to happen. And then obviously when we get with the extreme events, we then have the climate projections again to understand how these what extreme events might look like in these in the future. But again, as I say, there's this becomes a very probabilistic question around there's a inherently even larger level of uncertainty.
Yeah, that all makes sense. I guess, Sean, have you looked at, or has Colin potentially looked at any of the predictability of some of these extreme storms in the present period? So I don't know, could we predict an RWEN maybe 1 or 2 weeks out, or is that sort of beyond the scope of what's been done?
Colin's on the line, Sam. I don't think that has been done as such. The interesting thing is it depends on who the user of the information is. So when it comes to the energy companies, they say 24 hours ahead is fine because there's kind of 2 stages to it. They know that there's a storm coming, and so they can start to do stuff. And then just before the 24-hour, they'll start to ready linesmen. They'll actually get people deployed to regions where the extra storms are, and they share. So one of the electricity companies, say in the south, might send linesmen to the north. So just the one we had recently, everybody was over in Ireland. Yeah, so Cumbria got hit quite badly, but they didn't take any extra linesmen because they were over in Northern Ireland. The other one is the false positives. So they actually spend a lot of money preparing for these storms. So they would probably like that this is not going to be a big event earlier, because then they don't have to do any of those preparations. And if they get it wrong, then they're in serious trouble. But that's a longer time scale.
Sure. And I guess, Lizzie, when you're doing your work for the nuclear industry, they're not really forecasts, are they? They're more sort of projections of what could occur, or potentially worst case scenarios.
Well, we definitely are part of our adaptation plans for the nuclear industry. We tell them, there are different forecast methods out there and forecasts to use. So it is part of a risk review to see, what the companies are actually using. And then we can advise accordingly, depending on what the product's out there and what skill there is. But Sean's absolutely right in terms of the lead time that energy companies need. Because they're already fairly resilient and fairly well prepared. They seem to be happy with that short lead time that Sean said. So we do lots of post-event. We can do lots of post-event analysis from that. Certainly my climate team. We do have operational people that sit within the energy businesses that are actually running the plant as well, that take a slightly different view. But yeah, most of what I do and what we do is a post-event analysis and trying to help them with their adaptation processes and involve their different forecast products that they could do. I will say in my deep dark past in the radar group at the Met Office, I looked at the Boscastle event that happened. There was a really extreme flood that happened in Boscastle in Cornwall. And looking at the radar data for that was 1 pixel. 1 pixel is 500 meters. And like the whole of the radar going in the deep dark past now is something like 250 kilometers all the way out at the Bradanic radar down there. So you are looking at 1 pixel in a huge arc that actually gave this really, really extreme event that happened from this really, really convective system that came in. So you might not necessarily spot that particular type of cloud, very, very tall, like hammerhead cloud that comes through. So they are very, very hard in terms of extreme rainfall to see and to be able to predict those great big lead times. So yeah, it depends, horses for courses, as to which extreme events you're actually looking at and how that affects your forecast skill.
Great, thanks, Lizzie. And I guess a final question for all the speakers, which Dominic has put in the Q&A. So a general question to all speakers: to what spatial and temporal resolution of weather and climate data do you usually have to go to for any energy industry applications? Is there a minimum resolution and that users typically want for their local problem? I guess we could start with Lizzie this time. Sorry, throw you back into it.
It's cool. I'm game. In answer, I'll take whatever is available and that I can trust. Same with the rest of my group. We use a vast range of data to do our climate risk analysis. We do usually go through a screening process first when we do our assessments, but if we're looking at really, really detailed site stuff, we take the best data possible that we can have the highest confidence in. And we tend to apply a multi-evidence approach because there are many different types of data sets, not only to inform the client in the round, but also to cross-check across the different data sets, because, you know, some of the really, really site-specific, say, flooding stuff, that is the latest climate modeling project that's come out, right? And it's hard stuff. And as such, there have been a couple of times where we've got a product out and it is maybe has some errors, especially to do with rainfall. So it's about catching those really, and not just checking them out. But again, we're incredibly data rich in the UK. So when we go further afield, do things like for the Asian Development Bank, it becomes a lot more, or like islands in the middle of the ocean, it becomes a lot more about comparing global climate models with satellite observations, with any observations that actually exist on the ground. Yeah, so short answer is we'll take what we can get, and the best that we can get spatial resolution, if we absolutely can, at height and on the ground.
Great, thanks. Katie, for the NESO work?
I think this is a really, really good and interesting question, because I think if you talk to a specific end user, they'll base it on what the decision. Effectively, they're always going to ask the highest resolution, both temporally and spatially, but whether physically plausible climate data exists at that resolution is another question. So it's really important to actually, and especially when it comes to demand, I think in general, energy companies are interested in hourly data because they're interested in peak demand, which happens at, say, 4 or 5 o'clock when people come home from work. And so they're interested in what the temperature is at that specific time. And in terms of like the spatial resolution, for example, if you're interested, like people might be individual assets, a really high resolution, spatial resolution, but the reality is we don't necessarily have weather and climate data at that resolution, and I wouldn't necessarily trust it if we did. So the question is how can we work with whoever is making the application to make sure that we're actually using the best data for the type of decision they're going to make. The example I gave with the integration of the depressors data is a really interesting one, because that was daily resolution and at a 60-kilometer spatial resolution. So normally energy customers would probably say that's a write-off, that's not high enough resolution. But actually, when we recalibrated the model to input that data, the performance of the model was still good enough to be able to use that data to make a useful decision from it. There are also ways I will add of downscaling that data set if you did need higher resolution data. But as I say, it's all about what is the application.
Definitely application specific. And I guess finally, Sean.
So I'll answer the second part first. Users want higher than highest resolution. Okay, they want 1 minute, 50 meters resolution. But it doesn't matter actually. One thing I forgot to mention is that the forecast UKV, the T+0 UKV, and the UKCP are all the same model. And therefore, that's why we get good results, because the biases to a certain extent cancel out. So if the model is predicting high wind speeds, the T+0 is predicting high wind speeds, the forecast is going to predict high wind speeds, the climate change is going to predict high wind speeds. Fragility curves are size dependent. So you have to aggregate. People will go on. So two things happen. You've either got temperature, where it's pretty much the same temperature over huge spaces, or you've got wind speed, which is incredibly variable, and that you're never going to pick up where that actual damage is going to occur. So you have to aggregate, and you have to aggregate consistently with all your different elements. And then it doesn't really matter. The bigger because we've done tons of stuff on this. If you go down to the 2 kilometers, basically everything is zero in terms of damage, because most things don't blow over. So you get millions of zeros. And then what happens is you start predicting damage on a 2 kilometer grid, and it's just your random number generator that is deciding where that damage is. So you have to aggregate, and as long as you do that consistently, the bigger the area, the less the scatter, but the less accurate the mean, I think it is. So there's a trade-off. I can't remember which one it is, but yeah, but be consistent. That's the important thing.
Thanks, Sean. And I think that brings us pretty much to time. So I'd like to thank all of our speakers today for great talks and an interesting Q&A afterwards. And yeah, I think that's all from me. Thank you all. Enjoy the sunshine.